Hi, I'm Mark Weitzman. Welcome back again to our path integrals. I do want to just discuss very briefly some easy aspects. One of the reasons why the path integrals are so important is that it's easy to see the classical limit of quantum mechanics. So to see this, what we have is we have something which is proportional, the amplitude, whatever it is, it's proportional to e to the I, the integral of L dt, or we could write this as e to the I s. I'll put that the h bar here. So we have something that's sort of proportional to some phase factor. And the classical, when we're in the classical regime, the action, this s, we might have an integral here. This s is going to be very large, so s over h bar is going to be large. And we're going to have like a widely oscillating phase factor, which usually ends up zeroing out the constructive, destructive interference, and so we get nothing. But when the phase is stationary, that's when the contribution adds up, and so we want the classical action to be stationary. Actually, the classical action is defined in such a way, when you go through the Hamilton approach, that it is stationary, and I'll show in a second how that happens. But so when S is stationary, we just get the classical contribution here. The others all zero out. So that sort of makes sense how we get the classical mechanics. So if you remember, going back to the more precise formulation, we had something like I, the integral dt, p del q dot minus, you had pq dot minus h. So if we want to make this stationary on the path, we could do first like del p, and we'll end up getting an integral I, the integral of del p q dot minus the partial of h with respect to p del p. No. Okay, I'm doing this wrong. I want to do del q here first. So it's p del q dot minus the partial of h with respect to q del q. That's the variation. Then we can do a partial integration here, and we end up getting minus p del q minus p dot del q minus the partial of h with respect to q del q. So this leads to the equation p dot equals minus the partial of h with respect to q. And you'll recognize that, of course, as one of Hamilton's equations. And then when we do the del p, we get I integral del p q dot minus partial of h with respect to p del p. And this leads to q dot equal the partial of h with respect to p. And that's the other one of Hamilton's equations. So requiring that the action be stationary is equivalent to Hamilton's equations, and it's equivalent to the path integral being evaluated, or the amplitude in quantum mechanics coming from the classical path. So it basically says the particle, you only have to evaluate let's say here, let's say this is the classical path. We don't have to worry about these paths and these paths because they all cancel out destructively. It's only the paths that are near the classical path that contribute to the amplitude. Okay. Now, let me go on to something else. When we have a free particle, so V equals 0, non-relativistic quantum mechanics, this is an exercise, one of the exercises you'll be asked to do in Stronecki's book. But this is often called, you might see this notation, K of B comma A, kernel. Sometimes it's called the Green's function, kernel. I don't know if it's E or A. Green's function. Those of you who have seen it in electrodynamics, also sometimes called the propagator. And I'm just going to write down what the answer is. It's a well-known expression, but it looks nice. I'll keep the H bar in here. So this formula, if you want, you could actually substitute this into Schrodinger's equation. Verifies that it solves the solution for the free particle equation with V equals 0. Okay. Now I have one last thing in this introductory material that I want to show you. Everything on the path integral that we've done, let me write it up again. I'll just write it as e to the I. This is all undefined because of this measure and everything. And I don't know, people have been working on it. I still don't think there's a rigorous mathematical theory for the path integral where it's well defined, at least in physics. But this is something that's called imaginary time. And here it will be much easier to define, sometimes called Euclidean time. So here we make a substitution like t goes to it, or like tau equals it. Now, when we have that Lagrangian, L is t minus v, q dot squared over 2m minus v. This goes into minus dq d tau squared over 2m minus v. So it becomes completely negative. This I dt becomes a d tau. So our whole path integral ends up being e to the integral of d tau. I'll put a minus sign here. dq d tau squared plus v of q. This is much better defined. It's an exponential of real quantities with a negative sign in front of them, so it converges much more rapidly. So a lot of times you'll see quantum field theory done in Euclidean time, and the hope is that you can rigorously define this, or you can calculate this, And then you do an analytic continuation. Back to real time. You reverse the process. It's not always, to be able to do this, it requires that singularities can be avoided, and I think we'll cover this later in the class. Something like a wick rotation. Here are the singularities, and we'll rotate like that. We can do it because the singularities are here. We couldn't rotate the other way. So I just want to just mention this in case you ever see things done in imaginary time and Euclidean time. Okay, so that's the end of this first part on path integrals. I'm going to come back and do a couple of videos showing how they're used just before we get into field theory, what Sugnecki does in the rest of this chapter. Thank you very much.